is this is the last lecture of the course. I guess since not so many people are here, I had better send that around in a mail so people don't come this afternoon and think we should have a course. Second of all, this afternoon's, the lecture this afternoon will be replaced by a joint lecture of mine and Deepak, and I hope you will be interested in it. I will announce it. It'll be next week or the following week at a convenient time. And I hope Sasha can make the video. It'll be convenient for all of us. Should be interesting. If you want to see a picture of this lecture, we will have two blackboards in some sense, and I will be discussing matters on this blackboard on the left and Deepak on the right, maybe. And he will explain things in classical and quantum mechanics in simple context of, for example, harmonic oscillator and so on, right? So, classical and quantum physics, but elementary, and I will explain the math, the related math. So we will go back and forth. I think it's an interesting experiment to see if it works and if people care. The reason we're doing this, I mentioned because we're on the video now, is that the reason for this, original reason, is that I am cooperating with colleagues and friends in Palestine. So cooperation with Gaza the university in Gaza, who I can say hello to because they're also watching these videos. And there will be a joint meeting there of the faculties of mathematics, of mathematics and physics, and their hope to establish some cooperation, as we have. We're just friends and talking a lot, but they would like to establish that cooperation, and we think that in order to establish that, one has to have a common language and a good atmosphere and so on. And I've done this for a long time, so they asked me to have such a lecture, and I asked Deepak if he'd be willing to help me, so we should have some fun. And that. Speaking of Deepak, also I'm working with a student electronically in Kathmandu. Now I have to spell it right. Kathmandu, D-U, to say it.
T-A-T-S.
D-U?
T-A-T-S and after K-A-T-S.
There's an H there?
Yeah.
Kathmandu.
Yeah.
You don't pronounce it, do you?
cut.
Do you almost hear it when you say it?
Cut.
No, yeah, you almost, it's got some. Yes, this is a very, his first name is AJ. And we've been working together electronically for quite a while now, and he's very interested in mathematics and the kind of mathematics I do. And he's also watching these videos. So it's really wonderful to have this kind of possibility. And so, hi AJ. Okay, so let's continue with the topic of last time. Let's review where we are. I spent a lot of time introducing these important classical compact groups. And I can say now, because I know the audience quite well, I will call them Lie, they are Lie groups. Of course, Lie, the name Lie is for the great mathematician, sophist Lie. Of course, you know, if you're outside mathematics or physics or something, you look at this, it's the English word for not telling the truth. So, so people ask me what I do, and I say Lie group actions, and they think there's something very mysterious about that. But Lie group means this, that is, G is a Lie group. It means it's a differentiable manifold. That means you have differentiable manifold. Let's just remind ourselves of this at the beginning. With the structure, which is the multiplication operation. The multiplication operation smooth, and the inverse operation also smooth. I never know if you really need all of this, but to be safe, these operations should be smooth. And all of these groups that I've talked about, so the orthogonal group ON, or the special orthogonal groups. Let's even write SON to get the determinant 1, SUN. And it's automatic here for a symplectic group to have unit determinant SU. These are the classical groups. These are compact Lie groups. So they're slightly better than just topological groups, not only slightly better, much better, because they have smooth structure. And you should, I should remark that it is a theorem, or proposition maybe, the structure is actually a real analytic. Actually, automatically, let's say. So Lie groups are automatic. Let me just state this carefully. Lie groups are, in fact, automatically with further ado, automatically real analytic. That means that the structure and the multiplication and all this stuff, manifold structure, it is all realizable as in power series development. It's not just some C infinity function. Okay, that's a very important fact. And you can check it's not. So you have these things. These are very nice compact Lie groups. And we saw an example. Well, of course, you can have UN and you can have ON and so on. I mean, I'm not so worried about the determinate aspect. But in the last lecture, alright, so this is the last lecture of the course right now, but I will be giving one more lecture on mathematics and physics.
Oh,
And I will send around the information to the students of the course. So in the previous lecture, not last, better to say previous lecture, in the example of the unitary group, because that's a very important physical example, we realized that they're interesting, important ordinary differential equations that arise, and that's really, in some sense, where all of this arises. And they are even, let's emphasize, they are linear. Probably because problems have been linearized, so maybe it's not realistic life completely, but important linear ordinary differential equations, and of the form I write it in real coordinates. Later I will just write complex. It doesn't matter. X dot of t equals. I will write an operator here, h times x of t. So where h is simply an endomorphism of whatever vector space we're talking about, v. So a linear transformation. And of course that's an ODE, but I always like to write the initial condition, x of 0 equals x 0. So you're integrating this OED, and that means finding the integral curves. It's globally integrable. Here's a beginning point, and you're prescribing the velocity of the curve at each point. And you can find such curves in a very good way. And the best way is what we have. This is a little bit blinding. The best way was what we talked about yesterday, which I think is very, very beautiful, is the solution of these ODEs. Solution is given by the exponential math. Given by, for example, x of t, wherever you are, complex or real, is equal to e to the t h. Now, as I said yesterday, I think most physicists and many people in applications write e to the ith, where I is, right? I don't want to do that anymore because mathematically that is not a good thing to do. So I really want to leave it like this. And of course that's nothing other than the power series development. And you check that in fact everything's converges, there's no problem. So you really have global, these things have global, can be globally integrated. This is, the t runs over everything, so a t can be anything you want. So you have global integral curves through a given point. That means the vector field is, which we've given here, is globally integrable. It's a wonderful thing. And so we have a desire new word that we write about mathematics, a desire, a hope that we can really, that the one parameter group action, you see this is a discussion of symmetry, that the one parameter group action, where is that? Is that here, huh? Maybe here. Oh yeah. One parameter group action preserves the geometry. And in the case that you're interested in physics, you saw maybe you're preserving some physical phenomena. So that means, for example, which I took last time, let's do that example last time. These one parameter groups, this is a group, one parameter group, for example, if VH is a Hermitian complex vector space, Hermitian, well, let me just write unitary structure because I want it to be positive definite, a vector space. With unitary group, let's say it's n-dimensional, unitary group UN, so it's an n-dimensional vector space. Maybe we write the unitary group as matrices in the standard basis when we did identify this was Cn. Then the desire, I said that the geometry should be preserved. The desire is translated in this case that this group of operators, now it's complex, so it's a complex vector, so I'm going to write this as z of t. This z of t equals e to the th preserves H, or preserves the scalar product. And we know what that means, i.e. it is a group of unitary transformations. I.e. it is a group, a one parameter group of unitary transformations. Subgroup of the unitary group of unitary transformations. And so that means, as you recall in matrix language, or you can make this abstract, but it means that thing, the involution, so this means that tau is the involution that defines defining the unitary group. It'll be a little bit more abstract now. K, which is the unitary group in this case, then tau of this one parameter group, it should fix this one parameter group. Should fix it. Well, that's interesting. Let us do this in, as I did yesterday, in concrete terms. So let's do it as if we're just thinking in terms of matrices or whatever. Tau of e to the h. Oh, I hope you don't mind here. We have transpose and t. It's a very confusing thing, right? Maybe it would be wise to change the notation. I don't want to change the notation. Well, let's in fact, we can write S here. It doesn't have to be T, it's T there and S here. It doesn't matter, right? So now we put And what we have to do here, minus bar transpose, inverse transpose, equals, the condition is that this equals e to the sh, and that we worked out yesterday. That means that a minus h bar transpose equals h. Now, in fact, let's just even say that tau sub star of h is this involution here. Yeah. So that is, I write lower star because in fact it's the derivative of this map. So if you look at it, it's just simply, you just differentiate tau. So I wrote this thing tau lower star. Now, physics don't like that minus sign as much as I do, but I'm going to say that so the irrelevant space, at least for mathematicians, the relevant space, yesterday it was a space of Hermitian operators or Hamiltonians, and that was Hermitian without the minus sign because physics people always put an I in here. And I'm not putting the I in there, so is the space, and now I'm going to write it as, and then now you have to bear with me, as a German U. So that's math frac U, and because it's harder for me to do this, maybe I'll underline it to remind. Okay, so that's math frac U, German U. Okay, or I'll even write it with an N because this is the space of all these H's, and so this is the space of anti-unitary operators. And I'm sorry, I say unitary, Hermitian. Operators. And the condition H, just to remind you of the condition, the good way to write the condition, is H plus H bar transpose equals 0. That's the way we write this condition. And so the space of relevance becomes the space of anti-unitary operators. And we know that the appropriate action of UN on one parameter groups is you just conjugate the thing. So if you have some one parameter group here, starting at the identity, you can easily see with your experience with manifolds that the tangent vector is H. And this thing is e to the TH. This is a picture inside UN. And you might have another one parameter group and you hope maybe that it should be conjugate. So how does the unitary group act on one parameter group? So you conjugates them. So it goes over here with conjugation. This is U, e to the TH, U inverse. So you have one parameter group and you have a conjugate one parameter group. Those are a lot of one parameter groups. Somehow, in some sense, they're all equivalent because they only differ by a conjugation. So we are interested in the induced action on little u. my terrible German little u. The space of anti-Hermitian operators. So in other words, if you have a one parameter group, e to the ht, or e to the th, and that you can check this tangent vector here is just h, and you conjugate it, and maybe I write conjugation u of an element u in a unitary group of e to the th of this one parameter group. What I mean by that is u times e to the th times u inverse. Yeah, that's the new one parameter group over here. This is then u of th. That's how conjugation acts. You see, everywhere I go, I look at a relevant group action. That's how conjugation acts on one parameter groups. Okay? In other words, u of e to the th equals, let's see what it is. Well, it's just conjugation, and conjugation of the exponential is conjugated the thing in there, so it's just very simple. U of h, and let's write it down, that's e to the t, it's just this conjugation. U of h, u inverse. So we see, and remember I mentioned last time that physics people like to write u inverse sometimes differently as bar transpose, and they don't like bar transpose very much, so they write u dagger. That's even a text command, dagger. Okay. So that's how things act on one parameter groups, and H is called the generator of the one parameter group. So it shows you how you act on all H. So we have a linear representation of the unitary group, and they write it as UN because it's n-dimensional, on German UN, namely, if you take u of a Hermitian, of an anti-Hermitian operator in this case, it's u h u inverse. So starting with almost nothing, we have a very interesting representation of the unitary group. Okay. This is called, it's linear representation of the unitary group. It's called the adjoint representation. Adjoint representation. And the way to think then is this. You have a map as usual, UN, German UN, to view the group UN. This map is called exponential map. You take an anti-unitary, anti-Hermitian operator, you take exponential of it, you get a unitary operator. This is a compact mysterious group. This is a compactly group. It has a lot of heavy geometry in it. It is very complicated if you start looking, for example, at topological invariance. It's very, very interesting, not trivial. It's related to odd dimensional spheres because it's somehow the natural operator on spheres. And the advantage is here that this guy here upstairs is very close because you get all these one parameter groups going down. This mapping is by far not an isomorphism or anything, but you're getting a lot of the structure here going on. But the main advantage of this thing here is it's a vector space. So this is a vector space, it's a real vector space. Now, it's completely clear real linear combinations of anti-Hermitian operators are anti-Hermitian operators. That is completely clear. All right? Well, there's an interesting thing here. I don't know the history of this, but I think it's extremely remarkable and extremely deep. Is you look at the simplest thing, you look at the action of a one-parameter group. You have all these one-parameter groups. Of one-parameter groups, sometimes you say one-parameter subgroups, because they're subgroups of the unitary group. One-parameter subgroups of the unitary group on this thing, the German U. In other words, you look at, let's write it down, E to the T, I'm going to write it down, E to the TH1, H2, E to the minus TH1. All right? Instead of just making a horrible commutation, you know, just with one. We're just, why not? Right. But that's an obvious thing to do. And it is also obvious to say, since this guy is a vector space, you see the point is this is a complicated compact manifold. This is just a vector space. This thing is going on in a vector space, right? And somebody had the great idea, probably it always comes from some physics, probably, don't know the background, that again if I differentiate this thing, of course, I'm interested in what's happening at the identity. So I'm differentiating this thing when t is equal to 0. That's everything going on at the identity, right? Right? And you differentiate it, and it's, well, this is analysis minus 1. It's a product rule. You differentiate the first thing, evaluate at 0, plus the differentiation of the second thing, evaluated as 0, and you see what happens is you have H1, H2 minus H2, H1. Right? You just differentiate, you see what the one parameter group is doing by conjugation, that's a natural operation, and you're interested in the differential of that operation. That is a completely canonical thing to study. And so you write this thing down, and you see it's very interesting that non-commutivity plays a big role here. H1, H2 is not the same as H2, H1. So there's something very deep going on here. And so somebody, probably at the turn of the, I don't know, this is called the Lie bracket of this thing, realized that you should focus on this. So, starting with the compact group, in this case the unitary group, we made all this construction. It's very interesting, I think. So the structure here in the German UN, the vector space, is somehow this structure here. So we isolate it here. If you have UN, and the structure here is just group multiplication, associated to that, you have German UN with this bracket. Right? You didn't have to think very long to do that. Right? And in fact, you go back and forth, and the going back this way is the exponential map. I think that's a very important thing. So, This is called the Lie bracket. And this thing together here, this guy here is the Lie group. I differentiate it all the time. If you're careful about what I just did, I really need the fact that that's smooth and I can do this stuff. And this Lie bracket, and this guy is called a Lie algebra. Okay. Now, isn't that amazing? You started with a highly laws of curvature. It's like a sphere, or a tower of spheres, very complicated thing. Unitary group, and suddenly you have the unitary group. And of course, if you have the orthogonal group with its multiplication, you do the same thing. You get its Lie algebra, ON, German ON, bracket. Get its Lie algebra, and it's connected by the exponential map. The orthogonal group, if you remember, was defined by tau of an operator, I don't know, t, is equal to t minus transpose. And that means here that the Lie algebra thing, tau of xi, I like to have xi in the Lie algebra, is equal to minus xi transpose. You see, it just sort of takes the multiplicative thing into the additive thing. And so this says that the Lie algebra here is defined by the equation xi plus xi transpose equals 0. And you see, you expect that because in the unitary case, it's just the complex version of that equation. There's no big deal. Right? Anytime you have an involution defining the group, you have an involution defining the algebra. And it's a big advantage that you've gone to the algebra because it's a vector space. But it's a vector space with interesting structure. So the structure of this bracket, is this. Well, it's bilinear, it's real bilinear. And it's alternating, so antisymmetric. When we say that, we mean antisymmetric. And the word you see, algebra, you say, what the devil? Where's the algebra structure? I mean, we have addition and so on, but where's multiplication? So we think of multiplication, A, in the sense of A times B. We mean by that, A times B is just this bracket. That's how you multiply. You don't multiply, well, the bracket is not so bad. It's AB, it's almost multiplication of the matrices, is this bracket. And so this is a wonderful thing, and the key thing is this. It's something called Jacobi identity, which I will explain. It says that A, B, C is equal to A, B, C plus B, I hope I get this right, A, B, C plus B, A, C. Now, you check it. But if you have some horrible identity in mathematics like this, you should try to understand what it means. And it means that this operator here, A, here, is a derivation. It's a derivative. A of the product of two things is the product of A of the first guy times the second plus the second times the first. That's called, this guy from Germany, what's this? The co-temporal of Newton, Leibniz, who really developed calculus at about the same time as Newton. Maybe not as, I don't know, I don't know about the history of that, Leibniz. And it's called the Leibniz rule, because it's a derivation. It's a derivative, and you're not surprised, because that's how it arrives. It's a derivative. So this is called Leibniz rule, and it's called the Jacobi identity in this theory. So, so anytime you have such a Lie group of transformations, and this can be made in general, you can sit down and think about it, the orthogonal group, the unitary symplectic group, and so on. The groups are defined by involutions almost always, particularly, well, almost always, and so you know how to define the Lie algebra with the associated involution. Right? So again, I don't want to beat this too much. You have the top line of that statement there. You go back and forth from the Lie group to the Lie algebra, and in fact, it's usually enough to understand the Lie algebra, so I'm going to discuss another example. Well, a concrete example. So let's do a concrete example. This is a completely general thing. Right? You can imagine that. It has nothing to do with anything. Lie group, Lie algebra, basta. Go back and forth between the two. You have to think a little bit, but it's very, there's no geometry. You lose the non-trivial topology by just looking at the algebra, but you can actually, in many situations, recover it from the Lie algebra. Something called Lie algebra cohomology. So let's look at an example of, let's look at SU2. Okay, SU2. So you have a matrix in here, T, and this means that tau of T, I usually should write sigma here, but tau of T equals T bar transpose inverse. And so T, the one parameter groups X of TH and is the one parameter group, and so I'm just repeating what I said before. It's a little bit boring perhaps. This means that this is anti-Hermitian. So we have that H is an anti-Hermitian matrix. It's anti-Hermitian. And we have here that this thing here, I write it really as the power series. We want this thing to have determinant 1, because it's in SU, and you should check that the determinant of e to something is e to the trace. Okay, so it's a very easy trivial calculation. Just do it with diagonal matrices and that's enough. So trace is the key thing here. We know here, if you do a little work here, you see that the condition is that determinant equals 1 is the same thing as trace equals 0. Okay, there's another reason that trace appears. For me, trace, when I first saw it, it seemed a very unnatural thing, but determinant is highly nonlinear, trace is linear. You see, it's again the standard thing. You have this highly nonlinear thing, determinant, and because you have you're upstairs in the Lie algebra, it gets translated into a trivial linear thing, trace. Determinant and trace. It's a wonderful thing. You should go to the Lie algebra. Oh, if you can. Yeah. So we have this Lie algebra, U in this case U2 German, math fact, is a set of 2 by 2 matrices H, such that H plus H bar transpose equals 0. And now let's use SU2 because I started with that, and so I need the trace should be 0. Okay. All right. So SU2 because SU2, if you have something with an S here, forcing determinant to be 1, you put S in the German S here in front of the U to emphasize that the trace is equal to 0. Okay. Well, that's pretty interesting. Let's see if we can write down all those matrices. It's only 2 by 2 matrices, so I mean it can't be that hard. Or so let's see here. So H, let's say H is equal to A, B, C, D. And then H bar transpose minus, it has to equal minus H bar transpose. So it's equal to minus A bar, D bar. No, have I done bar yet? Yeah, and then I'll transpose it in my head. So C bar, B bar. H plus H bar transpose equals, yes, that's very nice. So that's equal to that. So that says that A is purely imaginary. Right? A equals minus A bar. A equals minus A bar. D, of course, is purely imaginary, and of course, if you compute it out, it has to have trace 0. So D equals minus A. Right? And so let's see here, B equals C bar. Now I don't know, it's a question of what you want to write. Let's write that. So B, okay, I'll write it here. B, let's call B equals Z, AB, and let's say C then has to equal Z bar. And since I wrote C, it's obvious I mean complex numbers. It's arbitrarily complex numbers. So the standard way to look at SU2 as a Lie algebra is and I always look at this thing, and this has to be purely imaginary. And so it's I and minus I phi, and what did I say? B equals C A B Z bar. Yeah. And quite often this decomposition that I've implicitly written here, you will see is a very interesting decomposition, because I've isolated a rotational part. If you take e to this power, this is exactly the circle. Rotational part, and I split it up into rotational part and other stuff. The other stuff it's embedded in a totally real way, but because I have a bar here, but it's a copy of the complex plane.
I think it's minus C bar.
Yeah. Huh?
I think it's minus C bar. Minus C bar. C equals to minus.
Z equals.
C equals to minus C bar.
No.
No?
Oh yes, minus, because I I messed up there. Right, minus, I'm sorry. But the other thing is correct, right? So it's all right if I put this down here. Thank you. Okay, that's pretty interesting, right? That immediately you see a sort of an interesting, this is a copy of R rotationally, and this is some sort of translation. Very interesting thing. It has a famous name, this decomposition. Yeah. Okay. So that's really what the Lie algebra looks like. And now, very interesting, look at the action on the Lie algebra. It's not so hard. Look at the action of SUN, well in this case 2, on its Lie algebra SU2. Because that's what we talked about the whole time. The entire motivation for that is study that action. So let's look at it carefully. Okay? Let's look at it. So, let's look at this. And let's look at, we'd be very interested in this. Let's start looking at orbits. Let's look at the easiest orbit. What is the easiest stuff in this easiest stuff in easy piece of SU2, German, is the rotational powers, the diagonal matrices. Or, I don't know, that's the easiest stuff. So let's write here the diagonal matrices. So this is a diagonal matrices, diagonal matrices of trace 0. I'll just put one in here, just to remind ourselves of what it is. It's I, and this is corresponding to a rotation. It's corresponding to a rotation, right? And now a rotation, well, I'll just write this. X I phi, that's a rotation with some phi t, is a rotation. There's a rotation for all these things. So if you take x of this real thing, that's just the circle. Okay. So this guy here, fine. This guy here, we x to this thing. X of this thing, x of this guy, x of the diagonal. This is circle. This is S1, and as you know, S1 is a one-dimensional torus. S1 times S1 is a two-dimensional torus, and so on. Right? It's a one-dimensional torus. So we call this thing a torus. We write this thing as a torus, T, as a subgroup of SU2. Again, you start with the unitary group. You forget, you want to get rid of the determinant, you go to the special unitary group, and the algebra therefore has trace 0 stuff. And then you look at the simplest thing, you make some obvious decomposition, you make the simplest thing you can find, the diagonal matrices. Is that not life? You want to diagonalize an operator. Right? So you find the diagonal matrices, there they are. And you're very interested in diagonal matrices because when you take x of them, it's just the multiplicative diagonal matrices in the unitary group, and that's a torus. In general, that would be a high-dimensional torus, and so we call this a torus. And you check that T is a maximal torus. And now you're going to ask me immediately, what the devil does that mean? the word maximal means, if you wish, dimension. So if you have, there's no other bigger torus in the unitary group. The only tori in the unitary group are of dimension 1, circles. The only tori in the unitary, SU2 and SU2. Okay. And you will be extremely happy to know that all of the maximal tori are conjugated. So it says that every unitary matrix can be diagonalized. And that's what's going on in the adjoint representation. In the adjoint representation, you have some, and this is very exciting. You see, you can imagine if you were Sophus Lee or I don't know, Hermann Weyl also, but by that time everything was more or less clear, I think. You would be very excited if you say, well, I take an arbitrary element of the Lie algebra, Xi, and I know I'm supposed to act by Xi. I'm looking at the action by C by conjugation. So orbit, orbit by conjugation. By SU2 conjugation, by SU2 conjugation. And so you study this for a long time and you see where this orbit goes. And the statement is every operator can be diagonalized. So that says that this orbit comes in here and hits the diagonal matrices. It's not a very nice orbit, it should be sort of a circle here. But actually it'll hit the maybe it hits the diagonal matrices in more than two, it could hit, with eigenvalue maybe you could have eigenvalue hitting up there. Let me just put Thunberg ecological eigenvalue. You might hit up here lambda, minus lambda the eigenvalue, and actually you probably hit down here minus lambda lambda. There's no reason to believe you diagonalize to get a unique thing, right? It depends on how you diagonalize. The order doesn't matter, right? Yeah.
Can you explain again why we actually get a torus and not just a part or subset of the torus? Because
I'm trying to understand where the question is.
Oh, because if we say we take the exponent of this diagonal matrix, then in the first component we certainly get the whole circle as S1, and also in the second component we get S1, right?
Yeah, but
But we don't.
let me just write something and you tell me where to stop. I think you're talking about the exponential map, right?
Yeah.
So we're looking at, for something, and here's a physics thing again, let's put T at first, TIA, right? So what I'm saying is, you have the point here, IA, you have the matrix IA minus IA, and that goes to the matrix. Let me write it here carefully. That goes to the matrix e to the TIAT, the one parameter group.
Yeah.
But of course, about IAT, t equals 1, so at unit time, I get to the corresponding point of the circle at unit time. But this just is a rotation all around the circle. So you ask the question, now in that language, what was your question?
So each component we say is a rotation, or even the whole matrix is a rotation.
Each component in this example will be a rotation, but
Yeah.
the same rotation effectively, it's just the sign difference.
Is it?
Yeah, so we're very lucky here, we only have one dimension going on.
And how is that? How does then the one-dimension torus look like?
Circle.
Oh, it's just a circle.
Yeah, it's just this, e to the IAT.
Yeah, I was thinking of S1 cross S1.
Well, it could be in general, but it would be here if I hadn't imposed trace 0 or determinant 1. But that imposition in the case of SU2 imposes just a one-dimensional circle,
Okay.
and which corresponds to the fact that in quotes, maximal torus in SU2 which is the diagonal matrices in SU2, is just a copy of S1.
Ah, okay, and that is the torus itself. And then if you go to the next dimensional torus, it will be
Well,
S1.
let's even do that to pin that down. Now that you ask, I think it's a very good question. So let's do it in SU3, right? So you have diagonal matrices. It's going to be the same thing. It's going to be e to the I, let me write here, phi1, e to the I, phi2, e to the I, phi3, times the parameter. But maybe parameter, well, pardon me, Nicholas, let me do it the Lie algebra level first. I, phi1. You see, it's so much easier at linearized. Okay, those are the diagonal matrices in the Lie algebra. The Lie algebra, don't forget what the Lie algebra equation is H plus H bar transpose equals 0, and that just forces the diagonal matrix entries to be purely imaginary. Okay, so that's all it is. However, of course, if I'm in this special unitary thing, this trace has to be 0. So what that says is phi1 and phi2 are free, if you want to think, and then phi3 is equal to minus phi1 minus phi2, right? So it's a trace condition here. So really, you only have the freedom in those two things. And now you're taking x for that, and that'll be a two-dimensional torus.
Okay, yeah, that makes sense.
Yeah.
Okay.
So you see that the dimension in general, if it's un, will be n minus 1 dimensional torus. Okay? And since it is really, in general, you can prove that the maximal torus in general has this property. So let me just write it down. Let me say something again about this. I think I answered Nicholas' question, but I'm going to repeat it in general so you can have a little fun. Okay? So there are several points here. The orbits, if you are trying to understand the orbits, which you should, of SU2 on its Lie algebra of anti-Hermitian operators, then you should try, and you should try to parameterize them in a nice way. We talked about this, find a fundamental region or something like this. And in this case, I call it a slice. And it really looks like a slice in this case. So this thing here, it slices across every orbit. So this is a fact which you can check, is that it slices, this thing slices every orbit. So if you want to parameterize the orbits, you really only need to use this thing. Right? Okay, let me draw this picture again. This is such a fundamental picture. If you understand it for the unitary group, you understand it for all of life. Okay. All other groups that we've discussed, at least compact or what we call semi-simple and so on, exactly the same as this. So please try to understand this. It's very extremely beautiful and central part of a lot of important mathematics. Okay? So here's the setup again for SU2. So the setup for SU2. SU2 with Lie algebra. German SU2. Well, you have the Lie algebra, German SU2, and the exponential map, which for every element gives you a one-parameter group, with the big SU2. If you have an anti-Hermitian operator here, it gets mapped to E to that anti-Hermitian operator. Then you look at a matrix here in SU2 and you realize it's of a special form. A very beautiful diagonal part plus, Deepak corrected me, I'm sure you're right, off-diagonal part. This wonderful diagonal part, right, so phi is a real number. So this part here, we give it a name, German T. And that's easy to remember because E of that thing is a torus. So E, or X, of German T is big T, isomorphic to S1, is a torus in SU2. Then we make a little remark for SUN, same thing. We get I, big matrix full of rotations, but with the trace condition equals 0. This is T, German T, and X of German T is a torus. It's S1 to the nth power. Torus is a product of S1s. You can see you have all that freedom except the trace has to be 0, so it's just a product. Yeah. Okay. It's extremely interesting. And then, I don't know who made this definition, you have the notion of maximal torus, which I just said. Just what I said, maximal dimension, all right? Torus, the maximal dimension. And then I don't know who proves this theorem for K compact Lie group, any two maximal tori are conjugate. It's not hard to prove. So in some sense, it says that this a maximal torus is a unique thing because conjugation is some sort of trivial operation, are conjugate. Right. And you should think those are the diagonalizable operators, or already diagonal. Right? And you should think in physics that those are the energy levels, right? Lambda 1 through lambda n, the diagonals. And you should think also in physics, if you make them positive and the sum equal to 1, that they're individual probabilities. P1, don't call them lambda, call it P1, P2, and so on. Right? Yeah.
So what does it mean to be conjugate?
Oh, conjugate. I'm sorry, terribly sorry. Terribly sorry. We say A and B, I'm terribly sorry, I thought this implicitly are conjugate in K whenever there exists a small k in K so that A equals K B K inverse. Okay? And again, the conjugation action on the group is a group action, right? But it's a group action on a highly nonlinear thing. I say that over and over again. These groups are really, they're manifolds and they're wonderful, but they're highly nonlinear. You lift the conjugation to the Lie algebra, you effectively are talking about Lie bracket. This complicated structure at the Lie group level is lifted into the bracket structure in the algebra level. It's really very interesting, right?
Excuse me. So when we then say that the two tori are conjugate, that means that the whole group conjugates.
That's right. So, or maybe that's what he was asking, right? Two tori are conjugate if and only, well, okay. I'll put here T1. It's what you just said, Nicholas. But it's conjugate as groups. Right? So when that's the case, then you feel like the notion is well defined. It's independent, it's defined up to conjugacy well defined. Yeah.
Also, I think this would be
Huh?
this would be Sn n minus 1, right? We get n minus 1 divided.
Yeah. Thanks. So, right? And I guarantee you, you can figure this out for any compact group or Lie algebra that has been given to you by involution. You can sit down and figure out all of this. And I figured it out explicitly for the unitary group for you here. Okay? What you need to prove, then, is the following fact. Here is a maximal torus, say, in the unitary Lie algebra. Say, T is a maximal torus in the unitary Lie algebra, SUN. We've written it down here, so that means that matrices of the form as I wrote before. Trace equals 0. As Deepak just pointed out, and of course the image in the group is n minus 1 dimensional torus. So this is an n minus 1 dimensional vector space. And so this, I'll try to use the same colors I used before. What did I use here? I don't know. Oh, I can't use colors too much. Maybe green is good because I like Greta Thunberg. So this is the torus, green, and the statement is that every orbit, if you start with any element of the Lie algebra, SUN, any, doesn't matter, and you look at its orbit by conjugation, so K, C, K inverse, you can diagonalize it. That says that T is a slice, I said, I called it, it slices across the orbit. Now, you won't be able to diagonalize it uniquely because the permutation group of permuting the eigenvalues is realizable as conjugation. So you will have the possibility of other intersections of the diagonal matrices. Right? There is the possibility of other diagonalizations of these matrices, but not much. The key thing, and I'll write it in a minute, right now, is the intersection of each orbit is a Weyl group orbit. So you're very interested if you had this slice for the action, which is you want to parameterize the orbits. There are many reasons to parameterize the orbits. You want to parameterize the orbits exactly, and so you look at this for a long time, and you see that for example, in the case, let me just write down in the case. I'll write it again. Well, no, let's write it down in the case of 3. So phi1, phi2, phi3 is here, so it's diagonalized, right? But you can conjugate it again and get something like minus, you can get something like phi2, phi1, phi3. The permutation group is acting here, actually. A permutation group is acting by conjugation, and if you hit this slice in one point, then you can let the permutation group hit it, and you go over here with the permutation group. That's the reason the permutation group is playing a big role. In this case, the so-called Weyl group is a permutation group. It's simply the permutation group. It just tells you how you have to go all over this torus to get all intersection points. Okay? This is not surprising at all. But you have a very good parameterization of the Weyl group orbit. Let's call the Weyl group the Weyl group W of the compact group orbit. And the intersection is a Weyl group. Intersection is a Weyl group orbit. So the quotient of the Lie algebra, in other words, the parameter space for all the groups, so the quotient, so SUN modulo K, SU, let's write it here, SUN. That means the action, modulo the action of SUN. In other words, parameterizing all this orbit is the same thing as the maximal torus modulo the Weyl group, and this is the same thing as in this case modulo the Weyl group. Maybe I never know as permutation group sigma n or sigma n minus 1. Sigma n, I think. You can imagine, I mean, you have this, you can't diagonalize it uniquely with the order of the eigenvalues, you can't do that. But that's it, that's the only choice that comes into this picture. So that's a wonderful thing. You see how the permutation group appears. In general, the Weyl group is really, the Weyl group representation on this torus could be really non-trivial. I know examples of exceptional groups where it's really very interesting. But at least for the unitary group, you have a beautiful parameterization of the orbits on the Lie algebra. And that is a general theorem, what I just said. A completely general theorem for compact groups. Okay? Completely general theorem. And the other general theorem is every representation of the compact group can be found somehow here. That's what I was telling you at dinner last time. Okay, so if you understand this representation, you understand everything. And it's very simple. It's something Professor Penkov will talk about next semester, I'm sure, is that you could conjugate an anti-Hermitian operator and get it diagonal, right? Maybe you even know that already. I don't know if you learned about it a little bit yeah. And the same thing for the orthogonal group. You have an anti-symmetric matrix, you conjugate it, you get a diagonal. The same thing for the unitary symplectic group. You conjugate it, you get a diagonal. And what it's saying is that physics people love it. It's saying that the only thing important here is eigenvalues, because you're diagonalizing, and they know that the only thing important is eigenvalues. They don't even need to prove this, they know it, all right? But it's a key mathematical fact. Okay. Well, I will stop. This is a very natural place to stop, and so I'll stop for today. I'll be around for discussions right now, for example, and go to lunch. And then I have to finish off writing some letters of recommendation, but I'll be in my office after that, okay? If you need to talk to me. And I hope you send me little papers about this, of course. I enjoy giving it. And I'll send you a message when I know, when Deepak and I, that I raised, we're gonna give this special thing. It'll be in the next week or so. I just have to learn what Deepak is saying, so he's gonna explain to me. It'll be nice. So I'll let you all know about this, so thanks a lot.